Oil-filled transformers are indeed usable in data centers. They have been implemented for numerous years and remain a feasible option. However, critical aspects require consideration. Firstly, fire safety. Oil-filled transformers contain flammable oil, presenting a potential fire hazard upon failure. Consequently, these transformers must be housed within a fire-resistant enclosure and equipped with fire suppression systems. Secondly, environmental concerns. Oil-filled transformers incorporate hazardous materials that could pose environmental risks if released. Therefore, proper disposal at the end of their life cycle is essential. Advantages of using oil-filled transformers in a data center include cost, efficiency, and reliability. Cost-wise, oil-filled transformers generally have a lower purchase price than dry-type transformers. Efficiency-wise, oil-filled transformers exhibit greater efficiency, minimizing energy loss as heat. Reliability-wise, oil-filled transformers possess a proven track record of dependable performance in data centers. Disadvantages of using an oil-filled transformer in a data center include fire safety, environmental concerns, and weight. Oil-filled transformers present a fire risk upon failure. Oil-filled transformers contain hazardous substances. Oil-filled transformers are heavy, which can complicate installation. Dry-type transformers are often favored for data center applications due to their reduced fire risk. Dry-type transformers lack flammable oil, mitigating fire hazards. They also present a more environmentally conscious alternative and exhibit lighter weight compared to oil-filled counterparts. However, dry-type transformers typically come at a higher cost and exhibit lower efficiency. Regarding reliability, both oil-filled and dry-type transformers demonstrate reliable performance. However, oil-filled transformers boast a longer history of dependable operation in data centers and often exhibit greater resilience under harsh operating conditions. Ultimately, the selection between oil-filled and dry-type transformers for a data center hinges on various factors. This includes cost considerations, efficiency requirements, desired reliability levels, fire safety protocols, and environmental impact considerations. Oil-filled transformers provide a cost-effective and efficient solution, but introduce fire risks and contain hazardous substances. Dry-type transformers prioritize safety and environmental responsibility, albeit at a higher cost and reduced efficiency. When dealing with transformer failures, the key is to understand the different types of failures and how to address them. Transformer failures can be categorized in several ways, such as by the part of the transformer that fails, the cause of the failure, or the speed at which the failure occurs. Common parts that fail include windings, insulation, core, bushings, and tap changers. Causes can range from insulation breakdown due to heat, overloads, lightning strikes, or contamination. The speed of failure can be sudden, like a short circuit, or gradual, like insulation degradation over time. Some of the most prevalent transformer failure modes include insulation breakdown. Insulation is critical for preventing short circuits between windings. Over time, heat, moisture, and contaminants can degrade the insulation, reducing its ability to withstand voltage stresses. This can lead to arcing and eventual failure. Overheating is another common issue. Transformers generate heat during operation due to core and winding losses. If this heat is not properly dissipated, the transformer can overheat, damaging the insulation and other components. Overloads can also lead to overheating. Short circuits are among the most severe types of failures. They occur when there is a low resistance path between windings or between a winding and ground. Short circuits can cause very high currents to flow, which can quickly damage the transformer. Open circuits, on the other hand, occur when there is a break in the winding. This can be caused by a loose connection, a broken wire, or a burned-out winding. Open circuits can disrupt the flow of current and cause the transformer to malfunction. Core failures can also occur. The core is the magnetic circuit of the transformer, and it is responsible for channeling the magnetic flux. Core failures can be caused by insulation breakdown between laminations, mechanical damage, or excessive magnetizing current. Bushing failures are another concern. Bushings are used to insulate the high-voltage conductors as they enter and exit the transformer tank. Bushing failures can be caused by contamination, mechanical damage, or electrical stress. Tap changer failures can also happen. Tap changers are used to adjust the voltage ratio of the transformer. Tap changer failures can be caused by mechanical wear, electrical arcing, or contamination. There are several methods for detecting transformer failures. Visual inspections can often reveal obvious problems such as oil leaks, cracked bushings, or discolored insulation. Electrical testing can be used to measure the transformer's impedance turns ratio and insulation resistance. Dissolved gas analysis involves analyzing the gases dissolved in the transformer oil. This can provide early warning of insulation breakdown or other problems. Infrared thermography can be used to detect hotspots on the transformer, which can indicate overheating. Partial discharge testing can detect small electrical discharges within the transformer insulation. These discharges can be a sign of insulation degradation. Vibration analysis can be used to detect mechanical problems within the transformer. Online monitoring systems can continuously monitor the transformer's condition and provide early warning of potential problems. When a transformer fails, it is important to take immediate action to prevent further damage and ensure safety. Isolate the transformer from the power system by opening the circuit breakers or disconnect switches. Inspect the transformer for any signs of damage such as oil leaks, fire, or smoke. Implement lockout-tagout procedures to ensure that the transformer cannot be accidentally energized. Investigate the cause of the failure to prevent similar failures in the future. Depending on the extent of the damage, the transformer may be repaired or replaced. Repairing a transformer can be a cost-effective option, but it is important to ensure that the repair is done properly. Replacement may be necessary if the transformer is severely damaged or if it is no longer economical to repair it. Regular maintenance is essential for preventing transformer failures. This includes visual inspections, electrical testing, oil sampling, and infrared thermography. Regular maintenance can help to identify potential problems before they lead to a failure. Replacing old transformers with new, more efficient transformers can improve the reliability and efficiency of the power system. New transformers are often equipped with advanced monitoring and protection features. Installing surge arresters can protect transformers from lightning strikes and other voltage surges. Surge arresters can divert the surge current to ground, preventing it from damaging the transformer. Ensuring proper ventilation can help to prevent overheating. Transformers generate heat during operation, and proper ventilation is necessary to dissipate this heat. Maintaining proper oil levels can help to prevent insulation breakdown. The oil in a transformer acts as an insulator and a coolant. Maintaining proper oil levels ensures that the windings are properly insulated and cooled. Avoiding overloads can help to prevent overheating and insulation damage. Overloading a transformer can cause it to overheat, which can damage the insulation and other components. Keeping the transformer clean can help to prevent contamination. Dust, dirt, and other contaminants can accumulate on the transformer and reduce its insulation resistance. Regularly testing the oil can help to identify potential problems before they lead to a failure. Oil testing can reveal the presence of contaminants, moisture, and other problems. The NEC, or National Electrical Code, does not specifically prohibit the installation of oil-filled transformers indoors, but it imposes strict requirements to ensure safety. These requirements focus on fire protection and containment to mitigate the risks associated with the combustible oil. NEC Section 450.23 covers the requirements for oil-insulated transformers installed indoors. This section mandates that indoor installations of oil-filled transformers must be in a vault constructed according to NEC Section 450.41 through 450.48. These vaults are designed to contain any potential oil spills and to withstand the effects of a fire. The vault must be constructed of reinforced concrete or other approved materials with a minimum fire resistance rating of 3 IROs. This ensures that a fire within the vault will be contained long enough for fire suppression systems to activate and extinguish the blaze. The vault must have a liquid-tight floor to contain any oil spills. This prevents the oil from seeping into the ground or spreading to other areas of the building. The vault must be equipped with a drain or other means to remove any accumulated oil. This allows for the safe removal of oil in the event of a spill or leak. The vault must be ventilated to prevent the accumulation of flammable vapors. Ventilation can be provided by natural or mechanical means. The vault must be equipped with a fire suppression system. This system can be a sprinkler system, a foam system, or a gaseous fire suppression system. The fire suppression system must be designed to quickly extinguish a fire within the vault. The NEC also requires that oil-filled transformers be protected by overcurrent devices, such as fuses or circuit breakers. These devices protect the transformer from damage caused by overloads or short circuits. The overcurrent devices must be sized according to the transformer's nameplate rating. The NEC also requires that oil-filled transformers be grounded. Grounding provides a path for fault current to flow to ground, which helps to protect personnel from electric shock. The grounding system must be installed according to NEC Article 250. Although the NEC permits the use of oil-filled transformers indoors under specific conditions, many data centers opt for dry-type transformers as a safer and more environmentally friendly alternative. Dry-type transformers do not contain oil, eliminating the risk of oil spills and fire hazards associated with oil-filled transformers. Dry-type transformers also require less maintenance than oil-filled transformers. They do not require periodic oil sampling or oil changes. Dry-type transformers are also more environmentally friendly than oil-filled transformers. They do not contain any hazardous materials that could contaminate the environment. Dry-type transformers are available in a variety of sizes and voltage ratings to meet the needs of different data centers. When selecting a transformer for a data center, it is important to consider the following factors. The transformer's kVA rating must be sufficient to meet the data center's load requirement. The transformer's voltage rating must be compatible with the data center's power system. The transformer's efficiency should be as high as possible to minimize energy losses. The transformer's reliability should be high to ensure that the data center's power supply is not interrupted. The transformer's cost should be considered in relation to its other features. Oil-filled transformers operating at 480 volts to 208Y/120 volts with a 160 kVA rating can be used inside a data center, but must adhere to strict safety and environmental regulations, including fire-resistant vaults and proper disposal procedures. Dry-type transformers are often preferred due to their reduced fire risk and environmental impact, despite potentially higher costs and lower efficiency. It's important to evaluate the specific requirements and constraints of the data center when making the decision. Always consult with qualified electrical engineers and adhere to local codes and regulations when installing and maintaining transformers in data centers. In a data center setting, consider the following electrical design practices. Firstly, redundancy. Data centers demand uninterrupted power, making redundancy a cornerstone of their electrical design. Implement redundant power sources, such as dual utility feeds and backup generators, to ensure continuous operation during outages. Secondly, uninterruptible power supplies, or UPS. Integrate UPS systems to bridge the gap between power failures and generator startup, safeguarding critical equipment from voltage sags, surges, and complete power loss. Thirdly, power distribution units, or PDUs. Utilize PDU to efficiently distribute power to server racks, offering monitoring capabilities for voltage, current, and power consumption, aiding in capacity planning and fault detection. Fourthly, grounding and bonding. Establish a comprehensive grounding and bonding system to minimize electrical noise and prevent equipment damage from ground faults, ensuring a stable and safe electrical environment. Fifthly, harmonic mitigation. Employ harmonic filters or active harmonic correction devices to mitigate harmonic distortion caused by nonlinear loads like servers, preventing overheating and equipment malfunction. Sixthly, cooling considerations. Design the electrical system to support cooling infrastructure, providing adequate power and control for cooling units to maintain optimal operating temperatures for IT equipment. Seventhly, energy efficiency. Incorporate energy-efficient transformers, lighting, and cooling systems to reduce energy consumption and operational costs, contributing to a greener data center. Eighthly, monitoring and management. Implement a robust monitoring system to track power usage, environmental conditions, and equipment status, enabling proactive maintenance and timely response to potential issues. Ninthly, scalability. Design the electrical system with scalability in mind, allowing for future expansion and increased power demands without major disruptions or costly overhauls. Tenthly, compliance and safety. Adhere to relevant electrical codes, standards, and safety regulations, ensuring a safe and compliant data center environment for personnel and equipment. These practices collectively contribute to a resilient, efficient, and safe electrical infrastructure, essential for the reliable operation of data centers. When working with any transformer, it is important to understand transformer impedance. Transformer impedance is a crucial parameter that influences several aspects of power system operation and protection. It represents the opposition to the flow of alternating current within the transformer windings. It's typically expressed as a percentage of the transformer's kVA rating at a specified base voltage. Transformer impedance is composed of two main components: resistance, which accounts for the ohmic losses in the windings due to the flow of current; reactance, which primarily arises from the leakage flux that doesn't link both the primary and secondary windings. This leakage flux induces a voltage drop, effectively acting as an inductive reactance in the circuit. The impedance of a transformer is typically expressed as a percentage value on the transformer nameplate. For example, a transformer might have an impedance of 5%. This percentage is based on the transformer's kVA rating and voltage. The percentage impedance value indicates the voltage drop across the transformer at full load, expressed as a percentage of the rated voltage. For example, a transformer with a 5% impedance will experience a 5% voltage drop at full load. Transformer impedance affects the fault current level in the event of a short circuit. A higher impedance limits the fault current, reducing stress on equipment. A lower impedance allows for higher fault currents, potentially leading to greater equipment damage if not properly protected. Transformer impedance influences voltage regulation, which is the change in secondary voltage from no load to full load conditions. A higher impedance generally results in poor voltage regulation, meaning a larger voltage drop under load. Transformer impedance helps limit the inrush current that occurs when a transformer is initially energized. A higher impedance reduces the magnitude of the inrush current, minimizing stress on the transformer and the power system. Transformer impedance is used in coordinating protective devices such as fuses and circuit breakers. The impedance helps determine the appropriate settings for these devices to ensure proper protection of the transformer and the connected equipment. When connecting transformers in parallel, their impedances must be carefully matched to ensure proper load sharing. Transformers with significantly different impedances may experience unequal loading, leading to overheating and potential failure. Transformer impedance plays a role in determining the transformer short circuit withstand capability. This is the ability of the transformer to withstand the mechanical and thermal stresses caused by a short circuit fault. A transformer with a higher impedance generally has a lower short circuit withstand capability. Transformer impedance affects the efficiency of the transformer. A higher impedance generally results in lower efficiency due to increased losses in the windings. The impedance of a transformer can vary depending on its design and construction. Factors such as the size and type of core, the number of turns in the windings, and the spacing between the windings can all affect the impedance. When selecting a transformer for a specific application, it is important to consider the impedance and its impact on the power system. The impedance should be chosen to provide adequate fault current limiting, voltage regulation, and protection coordination. The choice of dry type versus oil-filled transformers often involves considering their respective impedance characteristics. Dry type transformers generally have higher impedances compared to oil-filled transformers of similar ratings. This higher impedance can help limit fault currents and reduce stress on equipment, but it may also result in poor voltage regulation. Oil-filled transformers, with their lower impedances, tend to offer better voltage regulation, but may require more sophisticated protection schemes due to higher fault current levels. Understanding transformer impedance is essential for designing, operating, and protecting power systems effectively. It allows engineers to make informed decisions regarding transformer selection, protection coordination, and system performance. When deciding what transformer to use, consider the application,